Welcome to our machine learning project about energy consumption prediction. Today, we are going to identify the different linear relationships between the different pairs of our variables or features. We will be able to understand which features we're going to retain for our modeling and why other features are not considered for our modeling. So without much ado, let's get into our job. So before we move on to a lot more processes, let me first review the different steps that we have already undertaken. So the first thing we did was we created our environment, then we read the data, and also we considered understanding the different data structures, and then we also did the data cleaning. We identified the null values and we studied the numerical distribution of the different variables that we have. Then we identified the correlation values of these variables or features, and then we dealt with outliers. So in that we studied why we retained this particular percentage of outliers and why we considered those outliers which statistically are considered really outliers. And then we also added features and we treated them. And how we did that was we considered the energy load by hour, weekday, weekly, and monthly. And we also made our assumptions that the consumption during the nighttime is less than that of the daytime, and also for weekends are higher than those of weekdays. And also we stated our expectations, and this is our expectation. And with that, we said that there's a correlation between the temperature and or humidity and the energy load. And also in our very last video, we processed and examined closely our new features. What we will do this time is that we are going to identify the linear relationship between the different features. So before we continue, please don't forget to click the subscribe button down there because we do have a lot of free data science lessons for you. We have deep learning mathematics, mastering machine learning algorithm, the different data science tips, the different data science algorithms, and a lot more. Please click the bell icon to be notified every time we have a new session. And please give this video a thumbs up. And don't forget to share this with your friends. Okay? Now, let's have this one. So if you could still remember, before we have come to this point, we set the values of our appliance to log. So let me first find that part so we could properly see it. So in this part of our processing, we set the values of our appliances to log. And we already discussed the rationale behind this one. It's because we could see that there are a lot of our values that are too big, and that if we would proceed to considering these very high values, then the result would be that there would be a great bias in our prediction. So that is why we used this log function. Okay, so now what we're going to do first, so we could see the real picture is that, and also we can make comparisons between the raw data and the one that is already transformed. So we will have this one. So what we have in here is that we're going to make a histogram of the appliance's consumption. That is, again, as what we've said, for the raw data and the one which there is already a transformation using the log function. So let me first run this. So now we have here the two histogram, and we could see the differences. Here is the one which is already transformed, the log appliance consumption. And here is the histogram of our raw data. So as you could see, there is really a great difference. So in this histogram, we could see that our data is really skewed. And in comparison to this transformation, we could see that the skewness is lessened and our distribution is more or less symmetrical. And maybe you would like to ask me, why is it that we really have to transform our data from this one to this one? So remember this, that we are using here the linear regression algorithm. And the assumption behind the linear regression is that there is this normality of distribution. And because there is this normality of distribution, this kind of distribution before the transformation cannot give justice to linear regression. And that's what I've said. If we're going to follow this one, then there would be a great bias in our prediction. And so with this, then this can always violate the assumption of normality of distribution. And this can greatly and negatively affect the estimates of our regression. So I believe that you already know by heart what we mean by normalization. And when we're going to make the normalizations of our data, of our values, because this is actually very important when we are faced by a situation like this one, right? So this is a must for a data scientist to really understand what normalization is and how and why we do that. And so because we have already set a more normalized version of our data set, then we are now going to identify the correlation of our features. So here in this case, actually, what we're going to do is that we're going to use the Pearson correlation for us to be able to identify the strength of linearity among the different pairs of our features. So let's have this one. So we have already done this one before. So let's run this one so that we will see. Okay, let's wait for a while. It takes a few moments. All right, now we have here our results. Okay, so this is actually too much big. Okay, so let's just make this one smaller. Let's just use 15. Okay, but actually you can just use your own size, but in my case I just use this one because I think this one is too much big. Let's just have this one. Okay, now this one is, I think, is better. So what we have in here is that we're going to find which one has stronger correlation with the energy log appliances. But of course, again, as what I've said, we could also see here the different correlations between and among them. Okay, okay, so we will identify now which of these features have the strongest or strong relation with log appliances. So this part is actually the first part of identifying the linear relationship that is also very much important later on when we do the modeling. So just have some patience in doing this one in your project. So lights has a strong relationship with log appliances. It has 0.26 score. Then we also have T2, which is 0.22. Then also we have T3, and of course we have T6, and then we also have hour, which is 0.33. So far it has the strongest correlation among all of these features. Then also we have T18 is 0.16, and then we have RH out is negative 0.23, but it is a negative relationship, but still it is stronger. And also we have RH8 negative 17. Then we also have RH6, which is negative 18. Wind speed has 0.09, which is of course also a bit stronger in comparison to others we have in here. Okay, now so we have now identified these features that are showing stronger correlation. So this time, the next step of understanding and identifying the linear relationship is that we're going now to identify which among them have a strong linear independence. Okay, now let's execute this one. And actually, this may take for some minutes to finish. So this will take for some time to process. And while waiting, you can drink some water or you can have some coffee because it's still processing. Okay, so now we have here our results. For this part, I just would like to point out that we've considered T6, the T2, the RH2, the lights, hour, the T out, or the temperature outside, the wind speed, and the T dew point for understanding the linear independence of our different variables. Based on these results, we could see that the temperatures in and out and the T dew point have linear relationship. So the T dew point, where is it? Let us see. Okay, it's the last. Okay, so we have the T out, and this one is actually the relationship between the T out and a T dew point, so it's actually higher. And also for the T6, the T2, we can consider that the relationship with T dew point is linear. So for this reason, we're going to use the temperature inside our room as feature for our modeling. And of course, additionally, we're going to use also the humidity and temperature from the room, which have the maximum correlation with our appliance's load. So these are the basic things that we have to really consider before we're going to make our modeling. So we first understand why we did the transformation, and also we identified the correlation of the features with our log appliances. And based on these correlations, we have also identified the linear independence of our features. And based on this linear independence, we've also identified which of these can be used for our modeling. And now, maybe the question you have in your mind is this: are we going to automatically use those features which show high correlation for our modeling? The answer to that is, while it is true that there is a high correlation, we must also consider our expertise, our experience with the subject matter. But then, of course, we must be always guided by the results of our processing. Do you want to know more about this channel? Please don't forget to click the card on your right screen, because we do have a lot of exciting free data science lessons for all of you. We do have mastering machine learning algorithm, the deep learning mathematics, the different data science algorithms, and a lot more. Here, you can always learn and upskill for free.